Hello everyone, welcome back. In this particular video, we're going to start talking about the reactions of alcohols. We're going to particularly focus on the substitution and elimination reactions of alcohol. So let's get started. We're going to start with substitution reactions of alcohols. And among the substitution reactions, we're going to look at reactions that convert alcohols to alkyl halides. Okay, so we're going to learn how to go from an ROH to an RCl. Now, this may also be a good time to just think about, review maybe some of the earlier material where you want to think about, okay, how did we go from an alkyl halide to an alcohol? Do I know of a reaction that would do that? Okay, the answer is it is an SN2 reaction. Just a quick refresher. Okay, so we're going to start talking about the substitution reactions, focusing on the conversion of alcohols into alkyl halides. And there are a couple of these reactions based on the reagent that is involved. Now, and these reagents are also categorized by, or the reactions and their mechanisms are based on the alcohol that is involved, okay? So first, we're going to look at the reaction with HX, okay, hydrogen halides. What happens when an alcohol reacts with an HX? Now, if the alcohol that we're dealing with is a tertiary alcohol, these undergo this reaction via an SN1 mechanism. It's probably more appropriate to call it an SN1-like mechanism, okay? Something similar to an SN1 mechanism. To exemplify this, let's start with maybe tert-butanol, okay? Tert-butyl alcohol. This molecule is tert-butanol. If we react tert-butanol with HBr, this would give us tert-butyl bromide. Or tertiary bromobutane, okay? Either ways, but it's going to give you this bromo compound, okay? So what is the mechanism of this reaction? Why are we calling this an SN1-like mechanism here? Okay, so what happens here is when you react the tert-butanol with the acid HBr, this is an acid, HBr, we know that's an acid. And so the alcohol here, this can act as a base, okay, because it has lone pairs on it. So we can do some acid-base reaction here. So the lone pair on the oxygen can get protonated, and it would give us the protonated alcohol along with Br minus. Now, recollect from earlier that we've seen similar steps before. And what we're trying to do here is we're trying to convert a bad leaving group, an alcohol, into a good leaving group, okay? Because if it's a substitution reaction on an alcohol, as we noted here, the hydroxyl group is getting substituted by, I think I should just generalize and write HRX. So the hydroxyl group is substituted by the halide. So it's a substitution. But we know that a hydroxyl group is not a good leaving group. And so essentially what's happening here is that the hydroxyl group is getting protonated, which converts it into a good leaving group. Now, once that this is a good leaving group, this can go ahead and leave. So this is where the mechanism starts looking like an SN1 mechanism, okay, which is or resembles an SN1 mechanism. So this will ionize, and again, you're breaking a bond. It's not going to be a very favorable step, but this would give you the carbocation intermediate. And along with that, it's going to give us water, because the OH2 came out as a water. And we do have the bromine or the bromide that we are carrying along with from the first step. Okay, so once this carbocation is formed, the bromide can come and attack it. And essentially, at this point, this is giving us the product, which is the third butyl bromide. Okay, so it is an SN1-like mechanism. It involves the intermediacy of a carbocation. And then you want to remember that carbocations, they can do some crazy things, right? So there's a carbocation intermediate involved. So rearrangements are possible due to the carbocation intermediate. And so you might get mixtures of products, okay? But tertiary alcohols, when they are reacted with HX, it's the reaction with HX, they will get converted into alkyl halides, okay? They will go from the alcohol to the alkyl halide. And this is just a very general reaction. So essentially, any tertiary alcohol would become the alkyl halide. So that's how tertiary alcohols react. What about secondary and primary alcohols? Okay, let's look at those. Secondary alcohols these react by an SN2-like mechanism. Okay, that means there is a backside attack that's involved here. Okay, so if we start with let's say a secondary alcohol, and you react the secondary alcohol, and again, this is an example of a secondary alcohol. Okay, a secondary alcohol, and I can put R groups here just to make it a general alcohol. So secondary alcohol, when you react it with a hydrogen halide again, because we're looking at the reactions of alcohols with hydrogen halides. Okay, when you react it with the hydrogen halide, your product is again going to be the alkyl halide. The hydroxyl group is replaced by that halogen, but the mechanism is now slightly different. Okay, it follows an SN2-like mechanism. So what exactly happens? The first step here is similar to that of tertiary alcohols, which involves converting this bad leaving group, the hydroxyl group, into a good leaving group. Okay, so the lone pair gets protonated. So that we have a good leaving group now. And along with that, we have Br minus. Okay, and now this is where the mechanism differs from a tertiary alcohol. So in a tertiary alcohol, what happened was, or what happens is, this good leaving group now leaves to generate a carbocation, and then the Br minus attacks or the halide attacks. Whereas in a secondary alcohol, what happens is this reaction proceeds by an SN2 mechanism. So the Br minus goes and attacks that carbon, which again, relating it to some of the terminology from alkyl halides, we can still call that alpha carbon because that's where the functional group is attached. So this is our alpha carbon. So the nucleophile goes and attacks the alpha carbon, and the leaving group leaves simultaneously. So the attack by the nucleophile and the loss of the leaving group, these happen in one step. And so by the end of this, you lose a water molecule. Okay, that water molecule comes out, that's going to be there along with your alkyl halide. So any secondary alcohol, when you react it with the hydrogen halide, it's still going to give you the alkyl halide product. But the reaction proceeds via an SN2-like mechanism. That's the key difference. But in terms of the product that's formed, it is still an alkyl halide. Okay. Going to the last one here, which is the primary alkyl halide. Now, primary alkyl halides also react, primary alcohols, these also react by an SN2 like mechanism, but these need a catalyst, actually not a catalyst, a Lewis acid is required for doing this reaction. An example being like zinc chloride. If you're doing a chlorination, then zinc chloride can be a great Lewis acid. If it is a bromination, you could use zinc bromide. But again, there are economic things, right, that you would want to keep in mind. The zinc bromide is relatively more expensive than the zinc chloride. So you can do a chlorination more easily than a bromination here. And we'll learn other methods that would give us the bromination product. Okay, so happens is if you have a primary alcohol, this can react with HCl in presence of zinc chloride to give the alkyl chloride this time, because we are using the zinc chloride and the HCl. And now what is the zinc doing here? So the zinc is a metal. It's Lewis acidic. It has a positive charge on it because this zinc chloride is basically zinc 2+ with 2 chloride ions. Okay, so the zinc has a +2 charge on it. So essentially the alcohol can attack that zinc chloride to bring us to an intermediate where the oxygen is now bound to the zinc chloride and the oxygen has a positive charge. So it is very similar to the intermediate that we saw in case of the secondary alcohol. The only difference is instead of the proton here, it's the zinc chloride that helps to make this alcohol a good leaving group. Okay, and once this happens, we have chloride around because we have HCl. So there's chloride around. So essentially, the chloride can come and attack this carbon, release that leaving group so that it brings us to the alkyl halide that we want. And in this case, plus what we're going to make is we're going to be making zinc chloride with a hydroxyl group on it. And this zinc would then have a negative charge on it. Now, that byproduct that's forming is is sort of irrelevant here. And that charge could be balanced by like another positive charge. It could be like another zinc, it could be a proton, something like that. It would go back to like zinc chloride, so it would become like zinc chloride and water. Things like that are possible. But the key here is that the zinc chloride helps to activate or convert this bad leaving group into a good leaving group. Okay, and then the reaction proceeds that way. So that's the reaction of the alcohols, the three kinds of alcohols, tertiary, secondary, and primary, with hydrogen halides. And they all convert the alcohol into the corresponding alkyl halide. Okay. Are there other methods that can be used for converting alcohols into alkyl halides? Let's look at those. There are other methods known. Okay. So the reaction with the hydrogen halide is one way of doing it. Other reagents that can be used for converting alcohols into alkyl halides, and these are substitution reactions. The other method that we can use is reaction with thionyl chloride. Thionyl chloride is SOCl2. Okay, and what this reaction does is it would convert your alcohol into an alkyl chloride. Again, an alkyl halide, but specifically an alkyl chloride. This reaction also follows an SN2-like mechanism. It follows an SN2-like mechanism. Now, the overall reaction here is, and this is applicable, since this is an SN2-like mechanism, this is applicable for primary and secondary alcohols, okay? Because on tertiary alcohol, we won't be able to do an SN2-like mechanism. So if I use the example of a primary alcohol, when you react this primary alcohol with SOCl2, usually in the presence of a base, okay? We need a base in this reaction, and a typical base that could be used is pyridine. You will get the alkyl chloride as your product, okay? The alkyl halide. So our alcohol is converted into the alkyl chloride. I'm going to put the structure of pyridine here. Pyridine is this 6-membered ring. It's an aromatic compound that contains a nitrogen in the ring. So what is the mechanism of this reaction? How does this reaction work? You know, how do these reagents magically convert the alcohol into the alkyl chloride? Let's look at the mechanism. And again, the whole idea here, since we are doing substitution reactions, is to convert this poor leaving group, the hydroxyl group, into a good leaving group. Okay, so when you have the alcohol, it can react with thionyl chloride, SOCl2. So the alcohol can do a nucleophilic attack on that sulfur. This double bond on the oxygen is going to open up, and it would give us an intermediate. This oxygen has one lone pair, positive charge. There's sulfur. Oxygen has a negative charge, chlorine and chlorine. Okay, so we get to that intermediate. From this intermediate, the oxygen lone pair comes back to form the double bond with the sulfur. And as that happens, one of these chlorines leaves, because we know halides are good leaving groups, okay? So one of the chlorines that's connected to that sulfur leaves, so it would bring us to an intermediate where we have the oxygen, sulfur, double bond O, and then a Cl on it. And this oxygen has a formal charge on it. Okay. At this point, and plus, remember, we've made chloride at this point. Okay, at this point now, the pyridine comes in, which is the base. The pyridine uses its lone pair on the nitrogen to abstract or deprotonate that hydrogen. That's going to put the lone pair back on the oxygen. That bond becomes a lone pair on the oxygen. And it would give us a new intermediate where the oxygen is connected to the sulfur, double bond O, and there's a Cl on it. Okay, now this intermediate here that we've made, this is very similar to like a Tosyl group if you examine. Okay, it's not exactly the same, but some of the connectivity here is reminiscent of the Tosyl group, which we know is a good leaving group. Okay, so essentially once we make this intermediate, what happens is the chloride here, okay, this can go and attack that carbon. And if you track that carbon, that's this alpha carbon throughout, okay? That's this alpha carbon. It goes and attacks that alpha carbon. This is now a good leaving group, so the electrons go over there. And once the oxygen goes and makes a double bond with the sulfur, this chloride gets kicked out. So eventually, this brings you to the product where the chlorine is now connected to that alpha carbon. And along with it, you would make sulfur dioxide. There will be chloride, and what I left out was the pyridine that got deprotonated here. So you're going to make a pyridine that is positively charged over here. Those would all be the byproducts. So this byproduct is going to form in this step when the pyridine deprotonates the alcohol. That's going to give us this that byproduct also. And in the last step, the chloride attacks, oxygen goes, makes a double bond with the sulfur, the chloride gets kicked out over there, and so we get the alkyl chloride product. So that's the mechanism of the reaction of an alcohol with thionyl chloride. Another route to make alkyl chlorides. Okay. Now it all depends on what reagent you use, because we just noticed, or we just saw that you can use HCl for making alkyl chlorides. So it really depends on what you're trying to do here, okay, or what other limitations you may have. Okay. One last reagent that will convert an alcohol into an alkyl bromide. Another reagent that can be used for converting an alcohol into an alkyl bromide. That's reaction with phosphorus tribbromide. This is PBr3, phosphorus tribromide. Okay, and what this does is it converts an alcohol to an alkyl bromide because we have the bromine in our reagent. And this also follows an SN2 like mechanism. So as we saw earlier in the thionyl chloride case, the chloride went and attacked that alpha carbon with the loss of the leaving group. So something similar happens here. So again, using the example of a primary alcohol, if you react the primary alcohol with phosphorus tribromide, the product that you get is going to be an alkyl bromide. Okay, so the alcohol converted into an alkyl bromide. Alcohol becomes alkyl bromide. Mechanism of this is simpler compared to the thionyl chloride reaction, but follows a similar sequence of events. Okay, so the alcohol attacks the PBr3. Attacks the phosphorus. One of the BRs, doesn't matter which one of the BRs gets kicked out, so that we get an intermediate where we have the oxygen, one lone pair, positive charge. This is connected to the phosphorus, which has Br and Br on it. And along with this, okay, there is a bond here between the phosphorus and the Br. And along with this, we've got the Br minus that was kicked out. And so after this, the Br minus goes and attacks this alpha carbon. That leaves. That's your entire leaving group here, okay? So again, that's the alpha carbon, that's the alpha carbon, there's the alpha carbon. Br minus attacks that alpha carbon in an SN2-like manner to give you the product. Along with that, you're going to make that part as your side product. So you're going to have the Br2 on the phosphorus, and the phosphorus will have a hydroxyl group. So those are some of the reactions, substitution reactions specifically, of alcohols. And the ones that we looked at are the ones that that convert alcohols into alkyl halides. Okay, we started directly from the alcohols. Now the last substitution reaction that's possible that we're going to cover, which is a more widely applicable reaction because you can make a lot of products, because the reactions that we looked at right now, they were all limited to converting alcohols into alkyl halides. Okay, but the other reaction is the tosylation reaction. Now, this is a topic that we've covered before. Okay, so using a tosylate. Intermediate. So essentially what we do here is we convert the alcohol. We can react the alcohol with Tosyl chloride. And again, pyridine is a great base for doing this reaction as well. Some similarity here to the reaction with the thionyl chloride, even in terms of mechanism. When you do this, your alcohol is converted into the Tosyl ester. So you start with the alcohol, you convert it into the Tosyl ester. Here's your alpha carbon. Sorry. And here's your alpha carbon. So your oxygen stays, the TS comes in, you got the Tosyl ester. And now once you have the Tosyl ester, you can react the Tosyl ester with any nucleophile, and that nucleophile is going to give you an SN2 type of reaction. If it's a primary alcohol or a secondary alcohol, tertiary alcohols won't give you the substitution. Okay, you can play under SN1 conditions there, but anyways, it will convert the Tosyl group or it will replace the substitute, the Tosyl group with the incoming nucleophile, so that the nucleophile is connected to that alpha carbon and you get the Tosyl group out. So that's something that we've already talked about previously, so I'm not going to go into the details here, but that's another strategy for doing substitution reactions on alcohols through the intermediacy of a Tosyl ester, or using a Tosyl ester as an intermediate. Okay, and the Tosyl ester is synthesized using Tosyl chloride and pyridine. And then once you've synthesized the Tosyl ester, remember that this Tosyl group is a good leaving group, so it behaves like a halogen. So I hope these reactions help. And in the next video, we're going to start looking at the elimination reactions that involve alcohols as starting materials. Bye.